In this video, I want to talk a little bit about vectors in terms of the form that we can write them in and something about their angles involving the law of cosines. So, first of all, there are a few ways to express vectors. We know that we can already express them as in this component form, where the top component represents the x dimension and the bottom component represents the y dimension. Now, oftentimes, the simplest, what we call basis vectors, are the I vector and the j vector. And the I vector is defined to be the vector 1, 0. So it points 1 unit in the x direction, 0 units in the y direction. The j vector points 1 unit in the y direction, 0 units in the j direction, in the x direction. So these are useful vectors. I don't often use them in this form, but here's another way you can think about it. So let's say that we have the vector 2, 3, which is a vector that's 2 over 3 up. We want to represent that in terms of I and j. Okay, so what we can do is we can split apart the vector into as many pieces as there are components. So because it has two components, the x and the y, we're going to split it up into two vectors. The first vector, you see we've basically extracted the x component, zeroed out the y. In the second vector, we've zeroed out the x component and put in the y components. If you add these back together, you still get 2, 3. Okay, well, I can factor out a 2 from this first vector and a 3 from the second vector and write it as 2 times the 1, 0 vector. Because remember, when we scale a vector, we scale both components. So 2 times 1 is still 2, 2 times 0 is still 0. And then we have 3 times the 0, 1 vector. So, well, by definition, this is the I vector. Here we've just used square brackets, but the curly brackets mean the same thing, the parentheses. So this is the I vector, so we can just replace 1, 0 with I, we can replace 0, 1 with j, and we've written this in component form. Now, these are identical, so notice how we have equal signs here. These all say the same thing. I frankly prefer this form, but some people see this form and prefer to use that. So we'll encounter both. In 3 dimensions, the analogy is the same. Except we have 3 what we call unit vectors. These are 1 unit long. 1 points x direction, 1, 0, 0. The j vector points in the y direction, 0, 1, 0. And now we have the k vector, which points straight up, and that's 0, 0, 1. Okay, so they're 1 unit long, and they're all perpendicular to one another. And we can prove that because we can see that their dot product between any 2 vectors is in fact 0. Okay, so say we have the vector 2, 3, 4. So we have 3 components. We'll break it up into 3 vectors, each of which only contains one of the components, 2, 0, 0 plus 0, 3, 0 plus 0, 0, 4. They still add up to give us that. Now I'm going to factor out a 2, a 3, and a 4, and write it in, oops, this should be a 1 right here. So let's make that a 1. Now let me do this. Okay, so that should be a 1 right there. So we have 2 times 1, 0, 0, plus 3 times 0, 1, 0, plus 4 times 0, 0, 1, and by definition, that's the I vector, that's the j vector, that's the k vector. So that gives us a way that we can write it. Now, dot products you might see in this form, again, I don't prefer doing it this way because to me it seems more messy. Here I can just see it's 1 times 3 plus 2 times 4 is my dot product, which I get down here. Here I have to kind of, look really hard at this, and I see 1 times 3. I have to multiply the I coefficients together, multiply the j coefficients together, and then add those products. So either way works. From the law of cosines, we derived this formula, which basically, if I have 2 vectors, and one of them is, I have this I vector, or this v vector, and this u vector. So let's just say that's a u, and say this is the v vector. Okay, and what I want to know is something about their angle. So theta is right there. Well, we could use the law of cosines. We can create a triangle here so that we have something that looks maybe like this. And so now, because it's not necessarily a right triangle, depending on what theta is, we have to use the law of cosines to try to reconcile the sides and the angles. So the reduction of this comes down to this, that the dot product between u and v is the magnitude or the size of v times the size of u multiplied by cosine of theta. There are really 4 useful cases here. This is actually very revelatory. It gives us a lot of information about the angle, and about the vectors themselves. So in the case where theta is 0 degrees, we know that cosine of theta is 1. So here's a graph of cosine theta, and cosine theta is 1. Okay, so what we're going to be doing is that means we can replace cosine theta with 1, and the dot product will end up equaling the size of u times the size of v. Okay, nothing super fantastic there, but it will end up equaling that. Furthermore, now, of course, the angle could be greater than 90 degrees, and so now we're focusing on this piece of the curve. And the important part here is that the output anywhere along this piece of the curve, whether we look there, or we look there, or look there, is always going to be somewhere between 0 and 1. So if theta is between 0 and 1, that means cosine theta, if theta is between 0 and pi halves, which that's just 90 degrees right there. Right, so if that's between 0 and 90 degrees, that means cosine theta is going to be somewhere between 0 and 1, excluding 0, excluding 1. So that means that with the dot product will end up equaling, again, that's the size, that's the product of the sizes, and then it's going to be reduced down. It's going to be scaled down because we're going to multiply that by cosine of theta, which is going to be a number between 0 and 1. Okay, so the key here, though, is that if theta is between 0 and 90, well, lengths, sizes are always positive. These two quantities are never going to be negative because the way we compute them is it's the square root of the sum of the squared components of u and of v. Now, if this is a number between 0 and 1, that means this is going to be positive, which in turn means that the dot product will be bigger than 0. And so anytime you compute the dot product and you find out that the dot product is bigger than 0, you know that the angle between the vectors is somewhere between 0 and 90 degrees. Okay, case 3. Case 3 is